Very few organisms live solitary lives. Most interact with others of their own species as well as with those of different species. They are also influenced by the characteristics of their environment. The study of how organisms relate to each other and to their environment is called ecology. The dynamics of populations, how fast a population grows, how large it becomes, what affects its growth, is an area of study called population ecology. Rabbits have always been the symbol for prolific mating. With good reason, their populations can grow quickly. On average, a female rabbit can have 6 to 10 babies, or kits, in each litter. The mating season extends over a 6-month period, and a rabbit can have 4 or more litters per mating season. So with these impressive numbers, why isn't the Earth covered in rabbits? A population of 2 rabbits increases as they mate and produce a litter. If adult rabbits successfully breed and no individual rabbits die, this population can increase 4-fold each generation. This population explosion is referred to as exponential growth. If a population has no restrictions on growth, such as unlimited food sources or ample habitat, its size can increase exponentially. Let's look at the exponential growth of this population mathematically, starting with one mating pair. The exponential curve follows the equation G equals R times N, where the number of offspring, G, will be equal to the rate of growth, R, which in this case is 3 rabbits per adult, times the initial population size, N, or 2. So in this example, G is 6, because the rate of growth is 3 rabbits per adult, and there were 2 rabbits in the initial population. After each generation, the new rabbits are added to the existing population, such that N in generation 2 equals G plus N from generation 1, or 6 plus 2, which is 8. The population follows an exponential curve that increases in slope each generation. Obviously, this cannot continue forever because other factors affect the growth rate of the population. Let's go back to the beginning and see what happens in nature. The rate of growth can also be calculated as the birth rate, B, minus the death rate, D. Let's assume that the average litter of rabbits per mating pair produces 8 babies. Out of those 8, 2 do not survive to adulthood. The rate of growth per the original number of rabbits was 8 minus 2 divided by 2, or 3 babies per adult. Factors other than mating success can also affect population size, G. Carrying capacity, K, is a limiting factor in population growth, as it represents the upper boundary of a population size in a particular environment because of limited resources. As the population begins to grow, resources are not yet scarce, and the population appears to grow exponentially because N is less than K. As the population size approaches the carrying capacity, in this case 20 rabbits, fewer offspring survive to adulthood, and the rate of growth, R, decreases as N approaches K. This is called logistic growth and is represented by a log curve on a graph. Eventually, the population will stabilize at the carrying capacity of the environment when N equals K and R is 0. Carrying capacity is an example of a density-dependent limit on growth. A density-dependent factor is a condition whose influence depends on the size of a population. It can be biotic factors, such as predation or sources of food, or abiotic, such as water supplies or habitat size. As a population approaches the carrying capacity, either the birth rate decreases or the death rate increases, or both occur. Density-dependent factors include predation. When the size of the rabbit population increases, there is more prey available for predators to find, and therefore they kill relatively more rabbits, reducing the rabbit population. Competition for food is also a density-dependent factor that limits population growth to the carrying capacity. As the rabbit population increases, there is less foliage available for all individuals. As a result, the mothers aren't as well fed, and they produce smaller litters and more rabbits starve to death. This decreases population size by reducing the birth rate and increasing the number of deaths. Disease or parasitic infections are also density-dependent factors. When the population is larger, there is crowding, and disease agents can pass more easily from one rabbit to the next, leading to reduced survival rates. Some factors that impact population growth are considered density-independent. Regardless of the size or stability of the population, density-independent factors will affect the growth of the population. Density-independent factors can include flooding, extreme temperature changes, spreading of pesticides or herbicides, or a meteor hitting this island. Surviving individuals of a density-independent event will carry the only alleles in the gene pool to repopulate the island. This results in lower genetic variability in the population that develops from these few remaining organisms. As we have seen, the growth of a population is dependent on many factors. To truly understand what challenges a population faces, you must look at both biotic factors, such as interactions with organisms and food availability, and abiotic factors like weather and environmental conditions. Both affect how fast and how large a population will be able to grow.